Generating an electric field in space. We're going to look at the Faraday law and see that a changing magnetic flux produces an electric field. Now here we have a region, a circular region with radius capital R, where the magnetic field is increasing going down the page. Now if we look at a circle that's inside this region, this is the top view, then I'm going to show you that we're going to generate an electric field along this circular path because the magnetic field is increasing. Now earlier we looked at a case where we pulled a wire out of a magnetic field region. So this magnetic field going through this area, see the area was decreasing that had the magnetic field, and when it was decreasing, a current was set up where if you put your thumb along this direction, your fingers point into the page, so it wants to go into the page because it opposes what you're trying to do. By pulling this out, you're decreasing the magnetic field flux into the page, and this sets up a magnetic field, this current, that goes to keep it there so it doesn't decrease. See, it's opposite. So if you look at this case, you can think of that if there's a wire here, you'll get an electric current going so that here your thumb points out of the page, and that's correct in this case because when you increase downward, you want your thumb to be upward, your right thumb to be upward, which means your current's going to go this way, counterclockwise, because you want to oppose what is happening with the magnetic flux. Let's use the formula. If we use the formula here, we calculate the circumference for the red circle inside the region, and this is little r. From the center to that red is little r. From the center to the outside is big R. So you want 2 pi little r to get your red circle, and the 2 pi little r is going to be equal to the d dt of the magnetic field flux through that little circle region, which is pi little r squared. And then by dividing by 2 pi r, one of the r's cancel, and this is your result. Now if you want to do the same thing for a radius that's bigger than the big R, well then in that sense you have to replace with big R, since in that case the big R is the flux that's inside your region. Now this R is bigger than big R, but that's where the flux is. So if I'm out here someplace with a big red circle, the flux is only relevant for the capital R, so it's B times pi capital R squared for the flux. And then when you do that, you have a similar result, but one where the r, little r, the variable, is no longer in the numerator, it's in the denominator. So when you divide here, the pi cancels like it did before, you get the 2, that's the similar part, but then the little r is in the denominator here, the little r is in the numerator. Notice that if little r equals big R, then these are going to be the same, which we'll show you here. So little r equals big R, that becomes a big R, and if little r equals big R, one big R cancels out. So the thing here is that you got this neat generation of an electric field in space, and what I would like you to take away from this is that a changing magnetic field, which is represented here in terms of a flux, but a changing magnetic field creates an electric field. And we don't see that opposite equation listed here. This is the piece that Maxwell adds. Maxwell adds the piece here down below where you can get a magnetic field with a good old-fashioned current, but he believed you should also get the magnetic field by a changing electric flux or a changing electric field, the counterpart to this. And because he added that piece, he became, let's say, immortalized by these equations now are named after him, and he further did a calculation that showed that the electromagnetic fields travel as a wave. Now that's coming later. For now, in preparation of that, I want you to understand this major discovery here, 2 parts. 1, a changing magnetic field creates an electric field, and the created electric field is perpendicular to the direction of the magnetic field. So here, the changing magnetic field creates an electric field, and that electric field is perpendicular, see, to the direction of the magnetic field. And that's a precursor to understanding how light will propagate itself as a transverse wave in space, with electric and magnetic fields being mutually perpendicular to each other and to the direction of motion. But that's a preview of things to come.